In this lesson, we will begin by looking at the materials from which aircraft structures are made, and we will look at the effects of corrosion on these materials. We will also examine the effects of a hard landing on the aircraft structure, and we will look at failure statistics and their effect on flight safety. We will finish the lesson by having a quick look at the maintenance methods employed to keep aircraft in a safe and airworthy condition. Modern aircraft are constructed mainly of aluminium and its alloys, with smaller amounts of steel and titanium for the major structural components. Composite materials are used extensively for more lightly loaded structures. Each material is chosen for its particular properties with regard to the fatigue strength, wear resistance, strength to weight ratio, fire resistance, and so on. Aluminium alloys are the most widely used metals for structural use due to them having a good strength to weight ratio. Duralumin is an aluminium and copper-based alloy which has poor corrosion resistance except when clad with pure aluminium. It has good thermal and electrical conductivity and good fatigue resistance, but it is difficult to weld. Aluminium-clad duralumin is the most popular material in use for airliner skins. Steel and its alloys are relatively heavy, but can be made very strong. They are used only where strength is vital and weight can be ignored, for instance, in undercarriage units. Titanium is much lighter than steel, but it is just as strong and can be used where fire protection is required, for instance in engine firewalls. Titanium has good strength, and it retains this strength and its corrosion resistance up to temperatures of 400 degrees Celsius. It is, however, expensive to produce. The SR-71 Blackbird was the first aircraft to make extensive use of titanium within its structure, paving the way for its use in modern fighter and commercial aircraft. The Boeing 777 uses some 58 tons of titanium in its construction. Magnesium alloys are also used, their principal advantage being weight. Magnesium alloy has an excellent strength-to-weight ratio, aluminium of the same strength being 1.5 times heavier. Magnesium alloy has poor elastic properties, so its use in primary structures is limited. It is often used in the construction of gearboxes. Composite materials are becoming more and more used in aircraft construction. They are made up from layers of fiber, carbon, glass or Kevlar, molded into the required shape with a hot plastic resin, which is normally epoxy. Carbon fiber reinforced plastic is used where structural strength is required. It can be produced with the same strength as an aluminium alloy, but with a weight saving of about 20%. Glass fiber reinforced plastic does not have the same structural strength, but is often used for fairings and non-load-bearing panels because of its light weight. Kevlar has very low electrical conductivity and high fire resistance. Aircraft cabin doors, overhead bins, and bulkheads may be built with honeycomb cores made up of Kevlar. Composite materials have good resistance to corrosion and can be easily formed into complex shapes, but their fatigue behavior is different to that of conventional metal alloys. Metal structures suffering fatigue retain their design strength up to a critical point, after which failure occurs very rapidly, whereas composites lose their properties gradually. Interest in composites for structural use is due to their high specific strength and specific stiffness, allied with their ability to retain these properties at high temperatures. The Airbus A380 uses a significant amount of composite material in its construction. The tailplane, for instance, is almost entirely constructed from carbon fiber reinforced plastic. Corrosion is the slow destruction of metal by electrochemical reaction. It is one of the most persistent defects found in aircraft. Rectification of advanced corrosion has been known to take thousands of man-hours. In fact, more than 10% of engineering downtime is spent in dealing with corrosion problems. It is therefore essential that it is recognized at the earliest possible stage, and that effective preventative measures are taken. When a metal is exposed to the air, oxygen in the air reacts with the bare metal to form an oxide film which adheres to the metal surface. This oxide film forms a barrier between the air and the metal surface, which can protect the underlying metal from further attack. A good example of this is the Statue of Liberty. It is clad in copper. This has developed a green copper oxide coating which protects the metal from the elements. With the exception of oxidation, all other corrosion takes place when the metal is in contact with water, either as a liquid or as water vapor in the atmosphere. Corrosion is mainly electrochemical in character and occurs in conditions that permit the formation of minute electrical cells in or on the attacked metal in the presence of an electrolyte. It will also occur when a difference in potential exists between the different constituents of an alloy, or where dissimilar metals are in contact with each other. The degree of corrosion is proportional to the amount of impurities in the water, the impurities being due to industrial pollution which has high sulfur content, or by airborne salt particles when operating over the sea. The resultant action is that the metal undergoes a chemical change. The attack may extend over the entire surface of the metal, or it may penetrate locally, forming deep pits, or even follow grain boundaries inside the core of the metal. The weakening effect can be aggravated by stresses in the metal due to external loads, or there may be residual stresses from the manufacturing process or method of assembly.